we are coming to the end of this in-depth lecture series. And we'll now talk briefly about so-called ENOI system. ENOI stands for Ensemble Optimal Interpolation, after Evenson first used this term in his 2003 work. It's not very good, maybe, name, but that's how it's called, Ensemble Optimal Interpolation. And what it is just use a static ensemble in your data assimilation. Because, as I said, in the real in-cave system, the propagation becomes really important. But now, what if you use static ensemble from long historic run, or static seasonal ensemble from a long historic run, and use it in update? Then you update your ensemble mean with this ensemble at each cycle, but you don't touch this ensemble anomalies which you store everywhere, so they remain the same for the whole run. In this way, you much reduce the computational cost of your system. You only have to propagate the ensemble mean, right? So only one instance of the model. And when you estimate ensemble covariance from your historic ensemble, people use scaling coefficient alpha, typically say 10, 20, 30%, or something like that. And your hope is that in each particular instance, in each particular moment of time and space, the covariances which are produced by this historic ensemble may be not exactly good. They may be actually wrong if you compare them with the covariances from a real in-cave system. But your hope is that they are correct on average. That the correction you are doing still improves your system. So your system is suboptimal from the very start. But if you have a lot of observations and make a lot of small corrections, your hope is that you push it in the right direction, so it still is on track. So what can we say about that? And I need to say that our system to pass is the only in-cave system in oceanography. All other systems, all other operational systems, and there are many of them, they all use in one form or another ENOI or even OI approach. And why? Why this happens in oceanography but not in meteorology? Because in oceanography, the size of the model is much bigger than in meteorology. So if in meteorology the typical mesoscale sort of radius is sort of order of 1,000 kilometers, then in oceanography it's maybe an order of 50 kilometers. So you need much higher resolution, and your model is much more expensive to run. And okay, so this is cost effective. You integrate only one instance of the model. It's very robust. So most systems perform rather well, and there is no danger of ensemble collapse. It's better than kriging because you may still have anisotropic covariance, and it's multivariate. Although Oliver Talagrand said that the kriging can also be multivariate, but usually it's used in the univariate form. And it's a popular practical option for large-scale forecasting systems in the oceanography. So I thought at this stage of running an experiment of the same system with ENKF and with ENOI, and I'll probably do that. Just to demonstrate how this works. Because initially, most people they remain skeptical. If this can work at all. So I've set up two identical systems. So they start from the truth field is the same, the derivations are the same, and the only difference is that one system uses ENOI scheme with ensemble size of 50, the static ensemble of 50, and another scheme uses NKF with ensemble of 5. So usually you don't use ensemble of 5. I run it here with very small localization radius because it runs faster, just to make it faster here. So we can see some progress in real time. And then we'll compare and how both systems. So I start both two instances of MATLAB and start both of them in parallel. Hopefully. They will go all right. My computer will not crash because of overheating. So I'm starting for one. So that's the first system. That's the quasi-geometric model. This first system is the ENKF system, while the second system is the ENOI system. I'll explain shortly what we do see here. Running them for a limited period of time. This chart shows the true field. And the dots here show the observations which mimic satellite tracks which move, which change from one simulation cycle to another. Here we see the analysis field. You may see how close the true field is to the analysis. This is the difference multiplied by 2 between those two fields. So you can see where the difference is the biggest between the analysis field and the true field. And in this case, this last window shows the ensemble variance. So that's where how the ensemble variance is distributed around the state vector elements. And this is the NOI system. You can see that the ensemble variance doesn't change. So what you see here is the historic ensemble variance. So the system will be run for, I think, already finished. Yeah. So right now both systems have finished on my computer, and what we can see for ENOI. So you saw that the time for running the system was roughly equal. But if you look at details, say when you run system with NKF MATLAB, it actually sums up the time needed for propagation and the time needed for assimilation, and it excludes the times which are needed to calculate and save statistics and do other housekeeping job. So we can look exactly how much time did each of these systems take. Say in this case, we can see that assimilation time is 36.9 seconds and propagation time is 34.7, so roughly equal time for propagation and assimilation in this case. And while in this case, the assimilation time is 37.5, so it had much bigger ensemble of 50, but inverting matrix of 50 is not a problem. So the assimilation time was didn't change compared to the ensemble of 5. And but propagation time here is 6.7 seconds. So it's much, much smaller than here, because the ensemble here is 1/5 of ensemble in that case. So the propagation time is only 1/5. And if you compare the RMS error, say the final RMS error is 1.59. Here it's 0.99. So it's 1.5. The final RMS error of this field is 1.5 times better than of that field. But visually, and you can probably see it from that chart, from charts from the difference. But visually, you do not see much difference between those two. So you can say that NOI, it ran not as good as NKF, but still it did a very good job. So, because all main vortices of this quasi-geostatic model are in the right positions and with the right amplitude.
So you're saying that it's better to use NOI than NKF?
If you can't afford NKF, the first thing you are thinking about is using NOI. But not all systems say in most cases you will be able to get away with NOI, which is much cheaper. But say in the case of the fast, why we are running NKF? Because as I showed, the correlations around the ice edge are very anisotropic and non-stationary. You can't reproduce them with static ensemble at all. So we have to use the full NKF. So you have to use full NKF in some circumstances. You have no choice. Right. So that's was NOI. Any questions on the NOI? So the next is a very brief overview of the so-called hybrid systems. So it's quite popular lately.
Sorry, I do have a question about
Yes,
that.
yes, please.
If you're basically building up a static ensemble from a period of history,
Yeah.
and it's important to use all the data available in the whole history, or is it possible that you could select, say, storm events?
Yes, that's what's called seasonal ensemble.
Right.
To make historic ensemble, but from the right moments of history.
Okay.
Yes.
Okay.
That's seasonal ensemble. Say if say in oceanography, if you use NOI, say some groups use seasonal ensembles. Say for summer, for winter, etc.
Okay. Right. Okay.
So there's very big body of literature lately from about 2000 on hybrid, so-called hybrid systems, and there are a number of reasons why people start consider using hybrid systems of all kind. Like, for example, you can try to improve the performance of your variational system by adding some dynamical covariances to your background covariance you start with. Or if you can't afford ENKF, you may try to add static ensemble to your dynamic ensemble and see what happens. Say, if you can't run dynamic ensemble with 100 members, may you still afford to run dynamic ensemble with 10 members and have a static ensemble of, say, 100 or 1,000 members. So, let's I put this because this is perhaps the first work which I've seen on use of hybrid system. In this case, it was hybrid NKF VDVAR system, and there also will be other works. And what these works are doing is blending the covariances from the dynamic ensemble and from the static ensemble with some blending coefficient beta. And it's possible to formulate this completely in ensemble way, in ensemble formulation, to give it an ensemble formulation. For example, if you keep your ensemble of dynamic anomalies, if you have ensemble of dynamic anomalies and you keep your ensemble of static anomalies somewhere on disk, then all you need to do is, when you make your analysis, is to use a combined ensemble which is formed like that, just from columns of each ensemble with some coefficients. And in this case, you will get this estimation for the total covariance with this blending. So, and we tried this as well, and we have a work published which investigated the performance of this particular sort of systems with this type of blending and how useful it can be. And our conclusion is that you can't get much, you can't expect much outcome from that. So what we saw is statistically significant but very small improvement of the blending system compared, for example, to the static or to dynamic system. So, and if you think a bit why this would be, you understand that this very formula is problematic. Say, if one of these matrices, for example, goes to infinity, which means that one of them is a static ensemble or dynamic ensemble, doesn't know much about the system, it starts to dominate the sum. While what you want is the most certain matrix to dominate the blended product. So what we have as a sum is dominating, is sort of works in the wrong way, if you understand what I mean. Yeah. So in this way, what variational guys are doing, and they actually try to add contribution from the dynamic ensemble in some way to their cost function. You can see. And here, effectively, so I put conceptually, because the details may differ, but conceptually, their inverse covariance is blended instead of the covariance. And in this way, in your system, the most certain matrix, the one which is most certain about the system state, dominates the sum, which is probably the correct way to go. So that's on the hybrid systems. That's just a brief sort of.
So is that hybrid being tested at ECMWF? Is that what they've been trying?
I'm not sure what's happening in ECMWF, but I've heard presentation from the office, and they're doing that.
Right.
So.
Got it. Okay, just a question on your formulation before we move to the next slide. So, AD and AS orthogonal there, or
no,
there's some sort
no,
of
like your ensemble members are non-orthogonal. Here, there is no relation. Now, the next slide is about estimating the observation impact in your system. So when you run your system operationally, you probably want to know what impact observations have at some particular moment of time, or what impact some particular group of observations have on your system. And there is a common metrics which is called DFS, degrees of freedom of signal, used in meteorology. So if you make, for example, a global analysis, it's just a number which characterizes what your what your simulation did. So that's a matrix for your data for your analysis, for the difference to the system that your data simulation made. And how it works. So in the context of NKF, you can calculate this as trace of gain by h, trace by h. So very simple. And what it actually is doing is, what we see here is a normalized SVD spectrum. So if we have the SVD spectrum of our covariance, like I've shown before, and now we normalize each mode to 1. Okay? So we boost effectively the variance of each mode to 1. And after that, we compare that. Say, if after simulation your spectrum changed, and as we say, it became lower and flatter in some way, say, something like that. In this sort of normalized coordinates, this may look something like that. Okay. And what DFS is in this sort of normalized coordinates is just an area between these two curves. So you can see. So the one consequence of this is that some mode here can be really small, can be almost 0, but it still can have sort of substantial contribution to the DFS metric. And overall, this is a very useful metric for analyzing the performance of a system. Why? Because you know that so theoretically DFS cannot be bigger than either number of observation, your ensemble size, or your state size. So it's smaller than the smallest of this number, all these numbers. So say if you run ensemble of 100 members, we probably want DFS through single assimilation stay below, say, 10, because to have it 100 would mean that the whole posterior, the whole analyzed covariance is 0. So you don't want to go as far. So another very useful metric which we use in Topaz, but it's not used to my knowledge elsewhere, is what we call the spread reduction factor. You can also call it a variance reduction factor. So we look how much the ensemble spread, the uncertainty in the system, the estimated uncertainty in the system changed during the assimilation. So what we calculate is the trace of the covariance matrix in the locations of observations, only in those locations, and compare this, compare the forecast trace and the analyzed trace. So, and say if we talk in terms of SVD spectrum once again, then this SRF is proportional to the difference between the forecast spectrum and analysis spectrum. And the difference with the other metric is that the relative impact of small modes is much smaller. So, and why is this useful? Is that this tells you how much the spread of your system shrinks. And you don't want it to be a big number, because we know that if for the analyzed covariance to reduce by a big factor, we need our system to be very optimal. And if this happens ever, probably our analysis will be wrong in some way. So we want to run our system in such a regime that SRF is always, say, in this case, that's this spread factor is probably below 2. So in this definition, if you have SRF equal to 0, means nothing changed. If you have SRF, for example, 1, means that the ensemble spread, standard deviation of the ensemble anomalies, spread by a factor of 2, which means that the ensemble variance, so the trace of your covariance, changed by a factor of 4, which is a lot. So, if you do global analysis, these two metrics are just two numbers, which tell you the impacts of that characterize your analysis. But if you do local analysis, you can calculate those for each local analysis you are doing, and then you can present those in spatial maps, like here, for example. So you can see here the North Atlantic, this is Greenland, and this is Arctic, and so this is the total DFS and the total SRF presented as spatial maps. So for each horizontal grid point, we present calculated values from the each in the corresponding calculated in the corresponding local analysis. So here you can see that the DFS is scaled in this case to 22 out of 100. So we consider 22 as sort of extreme, and you can see the locations where it happens. And SRF is scaled to 2, which is also quite extreme, which means variance reduction factor of 9. And you can see that even this happens in some locations, but normally they're quite small. And you also can see that those two metrics are quite different. Say, SRF is big in the very dynamic areas like Gulf Stream, like this equatorial, the area of the Atlantic equatorial currents, and over the ice edge. So those correspond to the ice edge. While SRF may describe lots of variability in lower modes, which not necessarily occur in the areas with high dynamic. And another point I wanted to make is compare, for example, the contribution, what this matrix tells us about contribution of some particular types of observations. Here is the contribution from assimilating of satellite tracks. So what it tells us, say that say satellite tracks. Okay, and the next slide is from assimilating sea surface temperature. So if you compare the just visually how this is different. Say if you compare DFS metric, it says us that satellite tracks have much smaller impact on the system than sea surface temperature, right? But if you look now at SRF metric, it will tell us it's probably roughly the same. Maybe, say, in most areas at least, what we are concerned with in our system, it's roughly the same. And we in fact argue that SRF is probably overall much more relevant metric for us. That in oceanography it's very well known that assimilation of satellite tracks is very important to get your system right, because it contains important integrated information about the state of, about the three-dimensional state of the system. So the elevation of the sea surface contains information about the ocean dynamics, about the about the actual about the tracers like salinity, temperature, etc., etc. In all 3 dimensions. So it's integrated, very important integrated measurement. So, any questions on this? Next, I will very briefly go through some system design issues. I don't want to steal it from sakov+talagrand, we should probably talk about this. But maybe make just several points. What factors do you want to consider when you design your system? And so when will I talk about this, I will have in the background that we are dealing with the chaotic nonlinear systems like in oceanography or meteorology. Because that's not necessarily true. So if you consider, for example, oil applications, they much closer to constraining aesthetic field or something to recover what actual parameters and what the state of the system is on the ground. There is not much dynamic, although the oil reservoir changes over time, but there is not as much dynamic as in our system. If you can, for example, consider a coastal model which tries to predict the wind surge, then this system is mainly driven by forcing and by boundary condition, and it's quite dissipative. It's not as dynamic as our system, so it will have completely different behavior and should be designed in a completely different way. But the first issue I would say one would consider is what assimilation strength we want to achieve. Say, if you draw symbolically your model trajectory through time, and so look what happens with your ensemble. So after the previous analysis, the ensemble spread increases due to the growth, the growing modes in the system. Then we constrain it in the second analysis, and do this once again, etc., etc. Of course, I've drawn this as continuous trajectory, but in fact, it's jumps at each analysis done in one way too. So the more correct picture would be that. So, but if we consider the evolution of ensemble anomalies only, say over a long period of time, you'll probably get some mean value what the spread of our ensemble is. And this means that this jumps in the overpropagation, the increase of the spread in the propagation, which is due to the system dynamics, should be compensated by the reduce of the variance during the assimilation time. So on average, and this means that when you plan, and as we said, we don't want our simulation to be too strong. We want it rather to be. We don't want our spread to reduce from that much to that little. We want it rather each time to use a smaller cycle and reduce from that much to that. So the relative impact of assimilation is much smaller. In this case, we may be much more confident that our system performs in the right regime. So, and to ensure that, you can see this is affected by the cycle length. So you should, the simulation cycle length, how your simulation cycle window, the length of the window compares with the perturbation growing time in the dynamical system. So what I try to say here is that
what do you mean by the folding time? Is it the kind of time constant of the expansion of the error?
Yes.
Yes.
Say the doubling time or E
or the E
Yeah.
amount.
Yeah. So normally you try to make your simulation cycle length smaller than the system doubling time. Like say, if in oceanography we typically have doubling time on mesoscale of about 2 months, maybe 1 month, and sometimes less. But we try to keep our data simulation cycle length, say, within 1 week. And there are indeed some much faster processes than this dynamic of the big mesoscale eddies. And some groups even try to reduce the simulation cycle length to 3 days, use smaller lengths, etc., etc. But not always you can do this. You can always do effort to consider issue how long my simulation cycle is if you have lots of observations to simulate. If you only have one observation here, you have no choice but run the system until this point and simulate here. What?
How is the simulation window related to predictability? Is that also a measure of how far into the future you can make a sense?
It's not directly related because with the given analysis you can run into the future as long as you want.
The question makes more sense in the case of variational assimilation, where observation to period of time is assimilated together. Really, an assimilation window with length is a real parameter of the system control.
No, but we are simulating all observations together in asynchronous way. So,
but in variational assimilation, basically the criterion is that the objective function is a unique minimum. So the non-linearity is small enough so that the objective function has only one minimum in practice.
yes. So yeah, but I'm sure Olivier Conrad will tell you much more about that. So, but I wanted to give the ensemble perspective on this issue. The next one is will I be able to constrain the model? So that's not the question which is very easy to answer until you actually try your system. But you can estimate the just roughly intuitively. Once you work out what your simulation cycle length is, how many observations do you have during this cycle? And you may know from the other side, you may have a feel how many, how big is the dimension of your model, locally or globally, depending on your system, and compare how those compare with each other. And here, a T big is the simulation cycle length, and tau is the model characteristic, sort of perturbation going down. So you probably want to be able to constrain from assimilation as many degrees of freedom over time. So the density of degrees of freedom you constrain over time should be probably the same or bigger than the density of degrees of freedom you lose from the model dynamics. That's just rough sort of physical talk, but and both are very hard to estimate other than to have some concept in your head and some physical feel. But for example, you probably can use DFS metric as estimate for degrees of freedom you constrain by the observations, for example, and try this to be bigger than the number of degrees of freedom you have in the model. And the next issue you want to consider is the ensemble rank. How do I set the size of my ensemble? How this relates to the localization values? So we already talked about this, but that's what we want to have is that the ensemble, the size of ensemble could be bigger than the local number of degrees of freedom in a physical system. And at the same time, you can't make your localization radius too small, because if you don't have dense observations, and not very often you have dense observations. If you don't have satellite observations, for example, which provide you dense field, then you can only meaningfully assimilate observations if your localization radius is greater than your decorrelation, than your model decorrelation radius. If, for example, your typical edge size is 50 kilometers, you can't use localization of less than that, because your edge shape will be completely distorted after assimilating these observations. And another issue is, which I didn't talk about before, but which is there, that you should compare what is the objection velocity in your model with the localization radius you are using. Say, if you use, in our case, localization radius, for example, effective of 90 kilometers. 90 kilometers. And if our simulation window is 1 week, and we simulate 1 week back, we must ask the question, where physically our observation, which we assimilate at this point now, we assimilate at this point, if you use local analysis, where they have been 1 week ago. And if you're in Gaussian, there's advection form, you must be sure that 1 week back, these observations within this radius. So you should also keep in mind these issues. So once again, very often you want to make your localization radius very small from the assimilation point of view, but you can't. There are some physical limits which restrict the value of the smallest localization radius you can use with this that assimilation window or with this physical system.
But this means you're going to use the observation twice
No, why twice?
because of the action.
No.
Try to see if it's remaining inside the circle.
No, we use assimilation only once. Say we collect assimilation, we collect observations over a week, right? So in a period, say there are some satellite tracks in a week's time. Say this was on Monday. Say this was on Wednesday. And this was say sometime Sunday. And we say assimilate on Sunday. So we have these three tracks. Say all of them say be within our localization radius for this very point. Okay? So I increase those tracks. Okay. So this was just on Sunday, right? But the question is, so if at the time when we assimilate this the Lagrangian sort of matter which was at this point, the water which was at this point at that time, already advanced forward by the current, right? So if there was some state of the system which this observation characterized on Sunday, then at the time when we assimilate this observation, this property of the system is characterizes the state elsewhere, because this water has gone. Okay? So we assimilate the wrong thing. We correct our system, but our system is different now. So we are doing the wrong thing. And we are doing right if our localization radius was bigger. But if you use too small, we should restrict the observations we assimilate even more than by pure spatial consideration. advection.
conversion factor, which
That's
converts
advection
space
advection
to time.
Advection speed.
Yeah.
Yeah. So
Okay.
so it's
So
can reach
velocity.
can reach 1 meter per second. And 1 meter per second means that the water travels 80-90 kilometers in 1 day, and that's not uncommon.
Yeah.
So
It's worse with the atmosphere.
yeah. So basically, here my notes stop, and I wanted to talk very briefly, maybe, because I only have 10 minutes left, about 4 more things. And the one is very important issue, practical issue I start with, is the issue of model error. You remember that in the Kalman filter formulas for the update of the forecast covariance, we had that the forecast covariance for the next cycle is the propagated analysis covariance, propagated as though the model was perfect from the previous cycle, plus model error covariance. And in all these lectures I gave you on this on the Kalman filter, I never said a word about this, because this is covariance matrix. We don't have it in the ensemble, in our ensemble, in an explicit way. It's just not there. So, and so, what does it mean? So, when we apply MKF as I shown before, this implies that we have no model error, but in fact we do. And for example, what happens if you propagate your ensemble forward and look at i's edge position for each member, and you have some spread? And then you look at observations, and the actual i's position is somewhere here. So what happens in this case? In this case, your assimilation will fail. So normally you want the reality to be within your ensemble spread. So there's quite big literature on the model error in the MKF, but to be short here, I just probably tell about what we are doing with this interface. And what we are doing is very simple. It's very simple conceptually. We perturb the forcing of our system in such a way that we hope our ensemble spread includes what can be there in reality. And this is a very simple concept, to perturb your ensemble forcing. And some other people try to add perturbations explicitly. So to perturb your ensemble members explicitly. And this is much harder thing to do, because when you do that, you don't know if you move your system to the right subspace, and you don't know if your perturbations are dynamically consistent. When you perturb forcing, you automatically enforce that all the effects of these perturbations are dynamically consistent, right? And this system of forcing perturbation itself, say interpass, it's very elaborate. It's quite extensive. We perturb surface wind, precipitation, cloudiness, radiation, and many other forcing fields. And this required us, this final setup came after many years of running this system. So that's not easy part to think, but that's probably the good way to treat the model error in the MKF, if you want to do it in practice. And you have to do it if you are to simulate real observations, not run from experiments. So that's the first model error. So the second topic I want to mention, I already talked about the instance, about the impact, how you can estimate one way or another the impact the simulation, the observations are doing for your systems. But how actually you can diagnose your running system, whether it's doing well or not? Because if you run a system in reality, you don't have a true field in your hand. You can't calculate RMS error as we do in twin experiments. So you have to compare statistics of your model ground with observations. You have no other way. And this is called in data simulation examining innovation statistics. So that's quite important. And innovation, I remind you, is the difference between observation and estimation of this observation. So we will cover this in the talks.
What was that?
We will talk about innovation.
Yeah, we'll take it.
So I will not go into much details, but I'll probably show you a real example of innovation statistics from our real system. So I will not go into theoretical details on that. So, and how this can be useful in practice. So this is one example of innovation statistics from a very long run of the system. So each point on the x-axis is one simulation cycle, and it's weekly cycles. Here you can see the years. So there are how many? 1, 2, 3, 4, 5, 6, about 350 or something cycles presented here. And what we see here is the first, the green line. The green line is the RMS deviation of the innovation over all observations. So this is for particular type of observations. And you can do that for different types of observations and see how your system performs in regard to this physical variable. So this is for ice concentration. And so we can see, for example, how RMS deviation of innovation, which characterizes how well our system constrains the reality, how it changes over time. And you can see some peaks here, and these peaks usually correspond to the ice and melting season in Arctic, because when ice melts, there's lots of variability. The dynamics is very strong. So. And you expect that the errors will grow, and we see that they will grow. So this is from the pilot reanalysis. Pilot means that we tuned the system as it ran. So some peaks are particularly big, and we made some modifications to the system as it ran. So, for example, we increased forcing perturbation, and after that it started to perform much better. Now, the red line here is the ensemble spread, how it changed over time. So the good thing we see here is that the ensemble spread usually increased, see it jumped up due to the model dynamic when the dynamically our system became less stable during the melting season. So, and this is very satisfying to see that our system responded correctly. very, very pale gray line here, you probably can't see it, is the number of observations to the power 10 to the power 4 assimilated each cycle. You can see that the number of observations increased in winter seasons because the ice coverage is bigger, reduced in summer season. And the dotted red line is the theoretical estimate for the sum of the ensemble spread and the observation error. So, and theoretically, this should match innovation standard deviation. So this red line, this dotted red line, which you surely can see because I cannot see it almost. So it's it doesn't completely match this green line, but it's very close. If you may look at my computer later, it's very close. But the point is that's how you can estimate whether your system performs right or wrong as it runs. That's a real example from operational system. And this blue line is the bias field, the innovation bias. That's mean the average mean overall innovation. If your system performs, if your model is doing right things, you want the bias to be close to 0. Right? So that's something. And so I think we finish at this point.
Thank you. Excellent. And are there questions? We should certainly thank Pavel for having such a making such a dedicated effort in teaching us the mathematics and also the real applications to weather forecasting. And we are very grateful for your contribution to this
Thanks
book.
for inviting me here. It was fun.
And there's of course more opportunities to talk to Pavel later today.
And so if you have, so this lectures my listening will be available online.
Mm-hmm.
And further in time, if you think you have some questions to me that I can answer, I'm very happy if you email me, either with NKF MATLAB package or with any other questions in regard to data simulation, in particular to the ensemble data simulation. So please do that.
Gustavo may have put them already online. Everybody check yet?
Yeah, they're online.
Very good. Let's see how this comes up. And then we have a short coffee break. Here we go. Yes, it's all online. All the talks are there. Very good. And of course, if there are updates or something, they can be corrected. And if any of you want to suggest misprints or something, I'm sure probably also will not be grateful for an extra info. More copy.
Yeah. I'm sure that
Yeah.
oh, it's
Oh yeah, you'll always find
Jag såg Innes jättegamla papper av det. 32. Men Kaos pratar om någonting annat än vad vi pratar om.
Kaos
there is I just remember one thing. In past schools we had the session where the students sit together with the teachers for like half an hour, and then run swaps after that. No, it didn't really have that. Or it didn't have to actually experience yet. I could. I would be happy to do that. Yeah. What I was planning on doing then would be I would be and so on comprehensive. Yeah. Okay. So the idea would be that we split the students into two groups. And there would be 2 times 20 maybe, 2 times 10. And then you would be sitting with one group. In this room, for example, we would arrange the table in a lounge.
And this is just
And then we can, yes, and then the student can ask questions and you can talk to them, yes. I think that actually gives us the good opportunity to learn more about this and also
so
your insight about students. And I should have really done this
substitute this form
in previous schools.
for the solution.
Yes.
So if you're out of course will be probably
because you're in your state vector, you've got
Yes.
data.
not likely to be done.
How do you know?
So in that case, you can also this is your basis to
Because
expand.
you've got this mass.
You also need to expand
So,
this out your termite you have decided already. So this is going to be an expansion. Because it's not
So they reorganise.
expansion would be much higher. And this is for value. Well,
Yeah, so you need to
single value proposition.
So,
This is the this is the coefficient expansion we're interested in. To say that the coefficient that's the largest has the most dominant effect on their system. So for example, I don't have any coefficient.
you know, it would be depending 1.1 to 1.5. But we can understand
For example,
Yeah, I think that's the main point, which is that like saying that the actual vector it may be actually but so in terms of drawing that local
So ideally, in all the extensions, the coefficient became higher order than before. It's not the case, so, but what it's saying, in addition to that, using 1, 2, 3 orders of extension is not sufficient. What those coefficients are saying is that
How much of that will happen is how much time will be left to the budget?
those terms are also associated. So this is sort of kind of, this is a way of
It's going to be at least 3 6. It doesn't exist yet.
what the colonists
But it exists.
yeah, I don't know.
Very least analyze data.
Interesting thing is, this is a case with two random variables. So this is the variance. We don't need to know what it is. Like this is input and this is input. This is input. This is what
It's actually the astrophysics.
This is like one-time integration with the But what we're saying is that you can think of the linear variance. I think that the minimum. Also, because the polynomials here are orthogonal. Well, it's something to do with that are dependent only on one or two edges. So we go back to the table here. So we can see that there are some.
So that
There's some scenario.
So you say when you
I say it explicitly that more than that.
So what we can do then is,
But I also explicitly mentioned that we're counting all these features. I think you're,
so this
if they
is
don't believe
dependent
me, this is,
variable
I will be able to go
1, 2, 3.
through this when
We see that they have different. They have
yeah, that we will have a meeting, I'm sure.
also
Will be called for
with advantage.
But this is what I have.
there was two
There's also a summary.
You see that habitual interaction of 1, 3, 1, 3, and 2, 3. You'll see that they all have distributions. And then you look at the magnitude.
It's a bit funny, but that's because we are specifically addressing points that are in the issue.
1, 3 has very small contribution to total system.
maybe I just need to
In addition to this information,
I have actually thought
the company more general system unless they
it would be nice.
it's a very simple
was that I
This
had
is
actually in that case several sessions.
because we're in a random physics.
In the
There's other three. teachers were able to visit the schools.
Okay, for how long? That would be like for 30 minutes, 45 minutes, longer.
You mentioned
Meaning then that for
we know it's one.
In this, what is the
Wrong. No, I spent much of it tomorrow after our lecture because
the best part of the and today we have fun.
incidentally, I was starting tomorrow. Yes. One lecture at 9 and one at 7. That's all right. It's on purpose. It's all right for me. I prefer that.
What time do you start?
Because, you know, there are only 2 lectures. One I get. For me, it's all right. Because actually that will be the final lecture.
just one?
And precisely there might have been questions. I mean, one final lecture. Many times setting different from what I planned in the so. I mean, 1 hour for time before the last lecture. For me, it's all right, but maybe it's not good for students.
I didn't actually think about that. Right. So maybe it's also mistakes. Yes, I think about this. All right. Can we continue?
Yes. But this is the simulation.
Okay, are we on? Roughly? Okay. In the past, when I was organizing schools of this type, I had also sessions where the school was split up into several groups, and the teachers were talking to these smaller groups on a separate occasion. And I haven't done this for this school yet, but I think we can do that this afternoon. So the idea then is that after coffee, we split the group into 2 people. We will be approximately 2 times 10 people, and a bit more. And then we have the first group will be sitting in this room, and that will be with Olivier. And in the second group, we'll be going to the house 12, which is has a lecture room exactly like this. And again, we will arrange the tables in a longish fashion, with Pavel being in that building. And then, after approximately a bit more than half an hour, possibly a little bit longer, we'll switch the teachers, and then I will come here and walk with Olivier to the other building, and then I will pick up Pavel from there and bring him here. What do you think of that? So then that way you get a chance to discussing and talking to the lecturers in a smaller setting, which can be very beneficial. And I realized that I should have done that already a few days ago, but I somehow didn't think about it. But you have it anyway. And also let me remind you of the dinner tonight. That will be at 6 o'clock, and it will be in the Alvanova building. We will have it at level 2, in the Argonova building. So that there's this biggish area which we will set up for dinner purposes. And so that is something which is also slightly new for me, so I'm very much looking forward to seeing how they will be doing this. But that is, I hope, will be a nice event too, which will mark the highlight of this school. So now we have the next lecture by.
Okay, well, hello everybody. So according to the program, I should speak of evaluation of assimilation algorithm at this stage. I speak of it this afternoon, but now I'm still going to say a number of things about evaluation and assimilation and adjoint methods. Do you have questions on what I've done so far? On the adjoint method, or on anything else spoken about so far? Oh, I think I can talk in the course of my lecture, if you wish. Okay, so. So the adjoint method, I'm talking now of the adjoint method more than of assimilation. It's a very powerful tool. Actually, I think that if one is interested of computing gradients with respect to a large number of variables, I think there is no competitor to the adjoint method. The adjoint method is efficient when you want to have a numerical process and you want to compute the gradient or the sensitivity numerical process with a large number of scalar inputs and one or a few outputs, and you want to determine the sensitivity of one of a small number of outputs with respect to a large number of outputs. To what is a given output sensitive to in the input? Very efficient. Of course, if you have the reverse problem, you want to determine the sensitivity of a large number of outputs with respect to a small number of inputs. The second thing is, of course, to do explicit perturbation of the input in question and to run your model with a small number of initial perturbations and to look at what the result is on a large number of outputs. If you want to know the sensitivity of a climate to increase in the atmospheric content of carbon dioxide, you take a model that you hope is reliable to increase the CO2 content in the model. You run the model and look at how climate is modified. But if you want to know to what a particular feature in the numerical weather forecast, for instance, was sensitive to in the initial conditions, the best is to use the adjoint method. Well, by the price to pay for that, and the price is basically large memory requirements, in the sense that, as I said, basically one, when using an adjoint method, one has to keep in memory any variables computed in the course of a direct integration which appear in a non-linear operation, whatever it is, because the derivative of the non-linear function depends on the value of the variable, and also needs developing, validating, and maintaining adjoint codes, which is not that's always perfectly possible. It does require resources, both in terms of time and of demand resources. As I said, quasi-mechanical rule exists for writing adjoint codes. I described that somewhat roughly, but I described that. And of course, software, which are called adjoint compilers, have been developed for doing that. Basically, you feed this software with the code written at the same Fortran, and it produces an adjoint code. But these software are not perfectly efficient, and so in particular, they don't compute adjoint till now as rapidly as an adjoint written by hand by an experienced person would. That's because the software don't easily have a global overview of the code to be jointed, at least not as easy as persons, as an human person who knows the code has. But still very useful for making the work, making it much more rapid. Such softwares I have not put names here. There is the Tangent Iowa compiler, which called now FOSFOpt, a company which was developed in Germany by Ralph Gearin and company and collaborators. Ralph Gearin was first phase. He worked in an academic context on oceanography and assimilation of observation oceanography, and now he has set up his own company in which basically you give him a code and money, and he returns the adjoint code. There is another software system which is called TopNAD, which then is in a purely, totally academic context in France at INERIA, close to Nice. INERIA is a French Institut National for Research in Informatics and Automatics. It's a French space agency. And there are people whose name have developed, the name, I don't remember the name, Laurent Ascoët has developed an adjoint compiler, which is called TopNAD. And then this was done in an academic context. When you get in touch with Laurent Ascoët or one of his collaborators, I can keep you interested in the web, find them on the web, and then you interact together in a kind of automatic academic atmosphere without having to pay. I can give you more information on that. Yes, often the best is often to write the direct and adjoint codes in parallel at the same time. Actually, when ECNWF, that was a number of years ago, decided to shift to variational assimilation, to change the assimilation system to variational assimilation. So they had to take their model and to take the adjoint, or at least to take part of the adjoint. I'm going to say more about that aspect later. I decided, let's rewrite the code from scratch. In fact, that provided the opportunity of introducing modification and improvement in the model. So, but this is what they did. Rewrote totally their model and the adjoint at the same time. Which, when you do that, is actually the most efficient. It's only writing the adjoint and at the very same time you write the direct code is only a small overload. I said yesterday something like 10%. While if you take a code and then decide I want to take the adjoint, then it will be terrible. It will be very hard. Especially if there is nobody left around to tell you what exactly okay. Okay, when, yes?
So the motivation for introducing the adjoint is to find an efficient way of solving the objective function.
Yes, in minimizing or computing sensitivities, independently of any minimization. And actually, because this question of determining the sensitivity of one output of a smaller number of outputs with respect to a large number of inputs can arise in other contexts than minimization. The particular output you want to know the sensitivity of can be, actually, take an example, can be, for instance, and it has been done in the context of numerical weather prediction. One particular feature in numerical weather prediction has gone wrong. A depression has not been predicted as being as deep as it has been observed afterwards. Who is the culprit? What is the origin of the error in the forecast? Well, one way to do it, but will not necessarily give you answer, but something that can be done, is certainly to look at the sensitivity of the particular feature which was badly predicted, the surface pressure in the area when the surface pressure became very low, with respect to all the inputs in the model, in particular the initial conditions of the forecast. This can be done. And that's a precise example for us, but this has been done at the Siemens development. And on a few occasions, it provided, it gave me proof that the bad forecast originated in an erroneous observation which had been introduced in the assimilation. Why? It was erroneous. But it was not as obvious from the observation as such, but it was erroneous. In fact, I already spoke yesterday of this problem of erroneous observations. The number of observations is large, but it is totally impossible to rely on the human forecaster to look at all observations and eliminate those were wrong. This must be done automatically, and it is only in very special cases there can be a system which gives an alarm and tells someone on duty to look at the observation and to decide whether it should be maintained or not. Another possibility also is to run two forecasts with both with and without the particular observation which can be contested. This is not done at present. It may be done someday in the world. But what I stress is that once you have an engine code, it can be used for other purposes than immunization. And this is an example. Maybe it's not the most convincing example. I could have taken, yes, one of the examples I did in the US when we found out full advance in security and pointed out the origin of the bad forecast. This is sensitivity. This was done in an old work by Juan Enrico and Tony Sabat of the cities of NCAR in the US, in which it simply computed the sensitivity by the model of the surface pressure at a given point with respect to all meteorological fields, a number of hours before. And this is the sensitivity of surface pressure at this point, which is right in the middle of the world. With respect to the model fields, and with respect actually to the U component of the wind field, the east-west component of the wind field, at level sigma equals 30.35, the 350 hectopascal level, 0.7,000 meters. And you see that the pattern is rather isotropic, and there is surprising. Obviously, there's a propagation time over 3 hours. The distance corresponds to the propagation time that is necessary for a perturbation in the U field to influence the surface pressure at this point. Very clear. And the distance is rather isotropic, not strictly, but we are looking for the U component of the wind field, that is the east-west component. And that can be easily interpreted as being due to the propagation of gravity waves. Well, to say a few things about atmospheric dynamics, which all of you will be fully familiar with. Among the various types of motion, in particular the various types of fluids. This one does not derive. It's not particular. Among the various types of motion, there are gravity waves, which are similar to the waves of the surface of water. For some reason, some mass of atmospheric fluid is concentrated and if it's high demand, and it will increases, and it will go down into the gravity and induce motion naturally. The atmosphere is compressible, so the lateral motion will not be as intense as it would be in a fully incompressible fluid, but still it will, and this will give this, which will propagate. And these waves, the fastest one, actually propagate with velocity, which basically is the velocity of sound, say the velocity of sound. And this is just propagation of gravity waves. Now, which are allowed by the model. Now, for some reason, for a deep reason, gravity waves are not very common in the atmosphere. And in fact, they have nothing to do with meteorology in the ordinary sense of the word. Nothing. Almost nothing to do with the occurrence and the evolution, in particular in mid-latitudes, of regions of high pressure and regions of low pressure, which evolve in time and which are at the origin of ordinary weather, sun or not sun, or rain or cloud and cloud. It's almost independent of the existence of gravity waves, which contain an amount of energy. Separate the energy between gravity waves and other solution and other motion, which is mathematically possible, a small amount. While in a sense, one could argue that they should contain 2/3 of the energy. I don't contest the third. You observe them physically in the vicinity of mountains, and also in the vicinity of very strong vertical motion, which are used by which are caused by convection. Convection in this context is what occurs where the surface of the ground is strongly heated, as happens in summer when the atmosphere is free of clouds and a large amount of the incoming solar radiation is observed by the ground, which then hits the atmosphere from below, and this can result in strong motion, which are associated with clouds which are called cumulus clouds, which are real towers, something like 10 kilometers high or 1 or 2 kilometers. And these are associated with very strong shine inside the clouds. It can be associated with rain and thunderstorms, actually, and slow descending motion, subsiding motion outside. And in the vicinity of these clouds, you can observe gravity waves. But except for that, they are rather don't really exist. And if one looks at the sensitivity, and they are both damped and dissipated in the atmosphere. And if you like dispersed and dissipated. And if you look at the sensitivity for 3 days ahead, then you obtain a totally different pattern for the sensitivity of the surface pressures at this point. And this is due to something else, is due to evolution of another type of motions, which are called Rossby waves, theory, and which are slight, with an oscillation of slight perturbation about the gyroscopic balance, which, I remind you, is the balance which exists in the atmosphere, in the latitudes, and the ocean too, a balance between, on the one hand, the pressure gradient force, which goes from high pressure to low pressure, and the Coriolis force, due to the rotation of the Earth, which is very important, which has a fundamental importance, for atmospheric oceanic motion. So there is an approximate balance between the two, with a direction, with consequences that since the Coriolis force is at a right angle with the velocity relative to the Earth, to the right in the northern hemisphere and to the left in the southern hemisphere, if you have velocity like that in the northern hemisphere, the Coriolis force is like that, the pressure gradient force is like that, which means that there will be low pressure here and the center high pressure here, and the motion is essentially rotation about centers of high pressure or low pressure. And slight deviation from its balance oscillates in time and produces what is called Rossby waves, which is also associated with the motion of its structure. Of course, the evolution is not purely linear, and this structure can amplify, be reduced, interact, merge together, be generated again, and there is a whole very complex processes. But this pattern shows the sensitivity of the surface pressure, I think at those points, to due at a range of 3 days, that is through motion of Rossby waves. Rossby waves. Rossby, Carl Gustav Rossby, actually was Swedish. For those of you who don't know meteorology, you know that Scandinavia, in the first half of the 20th century, later again, particularly in the first half of the 20th century, Scandinavian scientists played a major role in the development of meteorology. In Norway, there was Jakob Bjerknes, who first developed the theory of gravity waves, and he developed the Norwegian School for prediction and kind of model, conceptual model for the evolution of the atmospheric flow and for making actually weather forecasts. No weather forecasts played a very. And later on, there were a number of other people, in particular in Sweden. There were Carl Gustav Rosby and another man by the name of Bergeron, which sounded like a French name, but he was Swedish, who both played a very important role in the development of meteorology. Okay, so that's just to show that adjoint equations can be used for other purpose than minimization, for sensitivity studies. And in a sense, if you want to do a sensitivity study, but if you determine the sensitivity of one output parameters who are respective to a large number of input parameters, you need one adjoint integration. If you want sensitivity of 4 output parameters, you need 4 adjoint integrations. Okay. Now something different. Variational simulation minimize an objective function of this form, in which there appear terms, in which deviation from, for instance, current point from the background is squared and weighted, as I said, by the inverse of the covariance matrix. And the inverse of covariance matrix of the error associated with the background. Same thing here. Well, we have the inverse of the covariance matrix of the error on the observation Y. I told you in answer to the question of one of you that the observation vector is not a vector, but not really a vector, but actually a list of observations. But still, I didn't say it yesterday, before yesterday. You can give it a vector structure. I remember very well. A number of years ago, I had a student, it was journalist before, I think, who worked on that. And on the occasion of a defense of his doctorate, we had invited Pierre Morel, who had been my own advisor. And journalist spoke of vector. Morel, who didn't like, was the old school at the time, didn't like, potential vocabulary in mathematics, obscure language, words nobody knows what really they mean. He was totally upset by that. We speak of vector, but that's not a vector. When you mix together pressure and temperature and humidity, that's not a vector. And you are not totally enabled to define a length or to define an angle between two vectors. That's not a vector, that's just ridiculous vocabulary, pretentious, ridiculous. That was wrong, actually. It's possible to define, even though it is a list of physical observation, it is possible to define. Let us suppose I do a linear transform, for instance, on the observation vector. It is this situation work. You have weight components, for instance, at a given point, taken along axes, east, west, north, south, which are in a sense arbitrary. You may wish to rotate the weight components. Same component by using cosine and sine, that angles, the weight component in other directions. Change the local direction which you use for representation of the local weight. You may particularly wish that because in the associated part of the sphere, there is no one unique references for the direction of the axis. If you want east-west and north-south, if you use east-west and north-south component of the winds, then at the pole, what do? You have to change. And another thing, that is commonly done, you may have radiosondes which measure temperature. The balloon ascends for the atmosphere, it means the temperature for the depth of the atmosphere. And this temperature, using the hydrostatic equation, can be transformed through the linear transform into a vertical profile of geopotential. That is a GZ, where Z is the altitude, through the orthopic approximation. That's a linear vertical transformation. So, this can be that. Let us suppose I do a linear transformation, so that's y become ez for A, which is matrix of coefficient, which is initial. I do. So, R is supposed to be the covariance matrix of the observation epsilon on the from the error epsilon on the observations. And so, in that transformation, epsilon becomes something like A, that is eta, for the sake of argument, use quick lectures. One of the first book, the first book on numerical Weber prediction was written by an Englishman of the name of Louis Fry Richardson. Who knows about Louis Fry Richardson? You know? Do you know, Andrew? No, I don't know. Louis Fry Richardson, you know. Louis Fry Richardson was a somewhat eccentric character. He did many things in his life, but in particular decided to develop numerical Weber forces. He did that by hand. It was a few years after the end of the First World War, and he devised a grid, on the surface defined grid over Western Europe, took meteorological measurements for one particular day, interpolated them to the grid, and computed by hand the evolution of the weather over a 6-hour period. It totally failed. His forecast was totally erroneous, with change of surface pressure of the order of 700 hectopascals within a few hours. Totally erroneous. Nevertheless, he published a book at the time, referring when not too strict, and you could still publish a book and find a publisher to describe something which has totally failed. It's a very detailed book. It considers everything, the exchange of water between the vegetation and the atmosphere and so on. And among other things, he used the Latin alphabet for symbols, then the Greek alphabet for symbols, then the Hebrew alphabet for symbols, and then, having exhausted all of the alphabets, he shifted to the Coptic alphabet, and recognizing that not all his readers might be familiar with Coptic alphabet, whenever he introduced a new Coptic letter, he said this letter is to be pronounced in the Hebrew name of the head. There are many other things which are mentioned in his book. He considered was one of the difficulties of meteorology was so difficult is for lack of communication and understanding between people of the various countries, the various languages. So he advocated the use of the particular language for meteorology, Ido. It was not his invention. It was a kind of Esperanto. Only Esperanto survived, but in the late 19th, early 20th century, several of those languages, so-called universal languages. And on the other hand of his book, the book has been new printing of the books have been published since Richardson's time. And so at the end of the book, there is a lexicon of meteorological with the term between English and Ido. And I must say that if you know English or European language, Ido does not seem very difficult. But anyway, he advocated the use of it. And there are many other things about Richardson. He is more or less among other people, at the origin of the notion of fractals. He simply considered what apparently he looked at encyclopedia and he found in the Spanish and the Portuguese encyclopedia the length of the common border between Spain and Portugal was quite different. What it said, the same border. And he found that when you want to the case of Spain and Portugal and something like that, and you want to measure the length, you take a pair of condenses or a map and you found out, depending on how you take the angle of the condenses, how long the basic length to measure the length of the border, you find a totally different result. And you found out for the mini geothermal structure, actually length goes to infinity as you decrease the basic the standard by which we measure the length. Sorry for anyway. So here that everything. So here I have that eta equal a minus 1 epsilon, and you might be interested in calling eta transpose. That's a minus 1 epsilon times a minus 1 epsilon transpose. And here you have a transpose of a product of a vector, the matrix by a vector, and the transpose of a product is the product in the transpose taken in reverse order. So this is a minus 1 epsilon transpose a minus 1 transpose, which I write minus transpose, and then you take the expectation of that, and you find that the expectation of eta transpose equals a minus 1 p of eta of epsilon transpose a minus transpose. That is equal to a minus 1 r eta transpose. And if you take the inverse of that, e of eta transpose minus 1, you find that the inverse of a product of matrices is the product of the matrices taken in reverse order. You find a transpose r minus 1 r a. And then you take this expression here, y, I consider the expression when y1 vector transpose r minus 1 y2, or y1 or y2 are two vectors in the space, and you find that since y equals az, this will be y1 transpose, that is a z1 transpose, times r minus 1 times y2, that is az2. And this transpose, az1 transpose, becomes z1 transpose, a transpose, r minus 1, a z2. And here you have the a transpose r minus 1 here, and this is precisely e of eta transpose. So this is z1, e of eta transpose, minus 1, z2. So in z coordinate, the expression for this term is exactly the same, but in y coordinate. This expression is fundamentally invariant in exchange of linear coordinates. It has intrinsic meaning. It doesn't depend on which coordinates you use to express it. It is always the same value. As a numerical value, it is always the same, whatever the coordinates you use. It is tensor invariant. And so this expression, like that one, define on observation space and on state space an intrinsic, that is coordinate independent, scalar product. It has intrinsic significance. So you can define the length of the vector, like that. You can define a length, a square length. And from that it is scalar product, so you can define a length. You can define angles, contrary to what I said. You can define an angle by the cosine of the angle is the scalar product divided by inverse norms or divided by the norm of the two vector. And you can do geometry, you can do a orthogonal projection, you can have a sphere, you can do the whole of geometry on the basis of that. So these are really vectors. Once you introduce the covariance matrix, these are really vectors. And it also gives, so can comments for another aspect, an important thing when you use quantities, physical quantities which represent physical entities with different nature, is how do you compare them and how? Is a 1 degree error in the temperature forecast larger or smaller than a 1 hectopascal error in the pressure forecast? Obviously, there is no answer. There is no easy answer to that. And as far as we can wish, we would prefer to avoid using methods which are based on such a choice, on such a decision. But we would prefer not to use methods which require a metric in either state space or observation space. But the fact, once you introduce a covariance matrix in either of the two spaces, you implicitly define a metric by the scalar product, which has a name. It's called the Mahalanobis scalar product associated with covariance matrices. It's called Mahalanobis. You may not know who Mahalanobis was. He was an Indian mathematician and statistician who lived, he must have died in the 70s or something like that. He created the Indian Institute of Statistics, or Indian Statistical Institute, which is in world level. It's a major scientific institution still now. And so this has, once you introduce a covariance matrix, you implicitly introduce a norm. If a covariance matrix is diagonal, or more precisely, it uses coordinates in which the covariance matrix is diagonal. This amounts simply to scaling the various variables by their own standard deviation. So take y1 over sigma 1, y2 over sigma 2, and so on. Of course, even if the y's of different significance, once they're normalized by the statistical, the climatological standard deviation, it makes sense to compare them. More generally, what this says is that the really appropriate measure is not simply scaling by standard deviation, but scaling by the inverse covariance matrix, which means if there are correlation between the measurements between variable measurements, the proper scaling is not to scale those measurements by their own individual standard deviation, but to make the complete R, they take the complete R minus 1, which takes into account possible correlation. And of course there are correlations. If a satellite passes over some region of the Earth, observes the outcome in infrared radiation, the same instrument, the errors will be correlated over a short period. So the measurements made at a point in the measurements made 200 kilometers away the errors will be correlated, and will be all the more correlated if the raw radiance measurements go through some numerical process from post-processing of the data through some algorithm, which of course cannot be perfect, which contains error, and if it is the same algorithm you use, the error of the output of the post-processing will be correlated. So there are correlations between measurements, and this must be taken into account. It's not, but if you don't take it into account, but significantly increases the quality of the analysis. And then this automatically takes into account this correlation and actually define a norm in state space. So, contrary to what my former advisor said, this is a vector which has full significance. Okay. So it was just a remark, but I think it is important to fully realize this aspect.
So in practice, is every observation, is the correlation calculated for every set of observations?
In practice,
that a huge
a variance is assumed for each observation. For what I know of temperature of satellite observation, I don't know what the situation is everywhere. I know what the situation was at ECM and WF when we started using satellite observation, large scale, now a very large majority of observation of satellite observation. They were confronted with this problem of taking a non-diagonal R. And apparently, that was such a basic change in the way the whole thing was coded. But they decided not to take. But they decided to assume a larger error variance to the observation, which of course is a rather fishy way of doing the thing. But given the practical constraints, we found it was the best. I'm not sure heard that now they have now shifted to something in which there's a non-diagonal R, but sooner or later they will have to do that. They can't avoid that. And okay. For vertical measurement, radio sounds, but when taking account the correlation is very easy, and this has been done for the start. Either well, not exactly what we do, it's for measurements produced by radio sounds who ascend in the atmosphere. That's a much easier problem. So, but again, that's in this notion of Mahalanobis scalar products is useful. I've put associated with the covariance matrices. I've put in here in parentheses stencil because according to standard established mathematical terminology, these are more than matrices. The matrix is only an Euler number of numbers. They have intrinsic significance, like the matrices which represent an operator, when you change the basis of that transform according to a law which is not the same law. The law of transformation of a covariance matrix is this one, the one I've put here. When you have an operator, you do not have a transpose, you have something A minus 1, A minus 1, A, not a transpose. So that's why these tensors are called to be twice covariant, although they are twice contravariant, although they are actually covariant matrices, while an operator is said to be once covariant and one contravariant. It's mostly a matter of vocabulary, but once you are familiar with this vocabulary, it makes things very actually easier to understand this. Anyway, so that was a remark which I think is important. Another remark. To which degree is it legitimate to use with nonlinear model, nonlinear observation operator, for instance the radiative transfer equation, to which degree is it legitimate to use the methods which are fundamentally, when you look at the theory from which they arise, linear? Well, data typically are in the form, as I said, of a background, XB, plus additional observations, additional data. I say observation because in our problems, most often they are physical observations, but maybe not all of them, and in any case, they don't have to. They don't have to. Of the form y equal h of x plus epsilon. But now h of x can be nonlinear. And this is what I mean by putting brackets here. If h was linear, it would be represented by a matrix, and it would be simply a numerical product. Here, it's not necessarily some nonlinear function. That's why I put a bracket. And actually, in case of 4D, if you have a background at the initial time of the assimilation period, plus observation distributed over the assimilation window, then this operator, which links the observations to the state you want to estimate, in that case it is the state at the initial time of the assimilation window, includes the model, because in order to go from your controller variable, what you want to determine, that is the model state at the beginning of the assimilation period, to observations at a later time, you have first to integrate the model. So this H, now in case of 4D, includes the model. Well, these data are equivalent in terms of informative content to the background plus the difference y minus hxb. Of course, if you can go from this to that, and knowing xb, you can go from this to that. So you see, the information contained in this set of data and in that set is exactly the same. And what's the innovation? We can spoke, and Pavel spoke of it in innovation. What's the innovation? That is the difference between the observations and the quantity corresponding to the observations in the background. That's really the new information contained in the observation. To the extent that the new observation tell you a different story from the background, that's very interesting. And if the background is sufficiently accurate, sufficiently close to the real x, so that the difference in d you have y equal h plus epsilon, so d equal innovation equal h of x minus h of xb plus epsilon. And if x and xb are sufficiently close to each other, this can be approximated by h prime of x minus xb, where h prime is the Jacobian of h at point xb. Then, if it is possible, the estimation problem is linear with respect to the deviation x minus xb from the background. So here you have enough d which depends linearly on x minus xb, and of course we see x minus b minus x equals 0 plus and reciprocity. So you get a linear problem where in terms of a deviation not of a global field, but in terms of deviation from the background. And this is the tangent linear approximation, and if this is valid, then using a linear method is valid. Okay, so is that valid? Is that so-called tangent linear approximation valid? Well, tests have been done both directly, in which people have actually computed perturbations with the model, look at how it evolved, and look at how the evolution was different from a linear one. People have done that. And it turns out that for large-scale meteorology, let's say scales larger than 100 kilometers, then this is valid to ranges about 24, maybe 40 characters. But over a period for which, for instance, variational simulation is performed. For smaller scales, it is not valid as such a long range. The smaller the scale, the less valid. The smaller the spatial scale, the more rapidly small perturbations amplify, and the more rapidly nonlinear regime appears. The nonlinear regime setup. No systematic study has been made on that, but an indirect proof of the validity of this approximation is that variational assimilation is possible, and this practically useful. I don't mean it's not possible to improve on that, but it's practically useful. So it's the indirect proof of the validity of that approximation. Very few people actually would use a large amount of resources to check this hypothesis. You can consider that as a rather formal exercise, which always has been done. I did that with of mine a number of years ago. Most people consider it it's more useful to really improve the methods developed by trial and error and heuristic procedure than to spend large resources on this. Incidentally, extended Kalman filter, which Pavel described, explicitly does that by explicitly introducing the Jacobian of the model. I don't think extended Kalman filter has been used really in any meteorological, as such, in any meteorological or oceanographical application. No, it's a kind of theoretical tool. I mean, not fully theoretical, because it is an approximation in the first place. Replacing a difference which is relatively small by a first-order approximation. So it is, but it is the idea behind the extended Kalman filter. Okay, so that was the second remark, which I think is also useful. No, okay, well, I'm finished saying that. The so-called incremental approach to variational assimilation. Actually, if after listening to what I've said, listening to people what I've done, you decide to implement forever in your other model, do you have to first develop the adjoint of the whole model, and then the adjoint of the developed, which requires quite some time, validate it, and then take your chance with variational assimilation. It seems to be a large investment if you have, for instance, a student and you tell him develop the adjoint of a model. You may spend a number of months developing the adjoint without knowing where really that will lead him. So is there another way to proceed more progressively? Well, of course, one way to proceed more progressively is to start with very simple models, kind of toy models, check if the whole thing works satisfactorily on simple models, which are very economical and you can run very rapidly and you can write codes very rapidly, and then progressively take more and more complicated models. That's true. But when you come, like ACMWF did at some stage, now we're going to use variational assimilation, and we have a gyroscopic model, it is necessary to develop our code. So, I wait again. The model is of a form, the model. State at time k plus 1 equals state at time k, on which you apply an operator, which now, again, can be nonlinear. And not the model. I'm going to assume here that this is, well, okay. My situation is slightly ambiguous, because here, my notation is slightly ambiguous, because here, psi k is the model state. It's not necessarily the real atmosphere. The real state. In particular, if you have a model, this model may contain error, as the Pavel said in the lecture, so that even if you start from real psi k, the state psi k plus 1 produced by the model may be different from the real state at time k plus 1. Because the model, as a simulator of atmosphere, is not perfect. So here, this is the model bracket, not the real state. It's important to make the distinction. And now the first order perturbation to the solution of psi k is given by, you do a small perturbation of psi 0, and look at how this perturbation propagates in time. Now, one basic solution of the model. This originated from some psi 0. Now you put a small perturbation on that, and you have a small perturbation delta psi 0, and then a new model solution which is mainly for that. Observe that the perturbation amplifies with time, and so the first order evolution of that perturbation is given by what is called the tangent linear equation, where here you put the Jacobian mk of Jacobian fk prime of the model operator mk at point psi. Model operator in general can be nonlinear. And then, I said yesterday, we did before, but the adjoint equation doesn't use the Jacobian of the model, but uses the transpose Jacobian, which appears explicitly here in the equation. So that's the setting of variational assimilation. And I stress that this gives you the exact gradient of the objective function, whatever it is, with respect to the initial condition. This is, as long as computing the gradient and the first order derivative is concerned, this is exact. I stress it's not an approximate gradient. It is the real. Now, if you want to do that more economically, my mouse seems to be stuck. What is about time to succeed? I will stop at this point. Incidentally, I spoke of my calendars. Something to do? Still nothing?
Is it
One more.
rebooting?
Does anyone know what to do?
I have a MacBook.
PowerPoint doesn't respond. We have already. Oh, well, offline. You see? Tu regardes à l'écran. Ça va apparaître, hein, de faire quelqu'un. Ah oui, ça apparaît dans un format. Ah, d'accord, très bien. Okay, so it was there. Is there a possibility to simplify over that, on that? To make this computation with the same basic model more economical? Of course, there were things for said. Well, simplify the adjoint. Take a simpler adjoint with less things, with no radiation or much less radiation, with no precipitation, with no interaction on the surface between no exchange of moisture between the surface of the continent and atmosphere. Take a simpler adjoint. In the context of minimization, that's not the solution. Because then, if you do that, the gradient will be erroneous, and the minimization will fail, or very likely. In the context of physical sensitivity, I spoke about, that may be all right, because you want to compute a physical sensitivity, being off by 10 or even 20% may not be or really matter for 5%. If you want to do minimization, the gradient must be exact, because then minimization code believes is built on the principle that the gradient which is provided to it is exact. So if you fool it, well, the minimization will not work. So the solution is to simplify simultaneously and consistently both the direct perturbation domain dynamics and its adjoint. So keeping the same basic model, which is considered as being a realistic physical simulator of the atmosphere, even if it is not what it is perfect, avec the best available at least, the perturbation dynamic is modified to something like perturbation at time k plus 1 equals perturbation at time k times some operator gt, which is an appropriate simplified form of the perturbation dynamic, and which may be non-linear after all. But here you have many degrees of freedom by which you can simplify not the basic model, but the way the evolution of the small perturbation of a given model solution evolves in time. And you must do that consistently if you want to have a minimization that works on the perturbations of the basic solution and on the adjoint. So now the adjoint equation becomes that, where here you don't have the adjoint, the transpose of the Jacobian of the basic model, but the transpose of a simplified, and you have many degrees of freedom. You may decide not to put word moisture exchange or momentum exchange between the surface of the Earth, the ground, and the atmosphere in your simplified GK. You decide to ignore that particular aspect, that particular process, in the short-term evolution of a small perturbation. And this is called the incremental approach to data to radiation simulation. And to my knowledge, it is generally and maybe systematically used, implemented in weather centers where, funny thing, implemented where, okay, for devices for operational assimilation, at Météo France, this I know, and I think I never heard it. And this, so, if you look at a paper on assimilation, operational assimilation, you attend a seminar, and the man says, I'm using the incremental approach to variational assimilation because very standard, this is standard vocabulary. This is what it means. It means that the evolution law, not for the basic model state, but for a small perturbation to the basic model state, has been simplified. And thereby many degrees of freedom on deciding what to want to include or not to include in the evolution of a small perturbation. Actually, this may even be iterative with increasing complexity in G. That you have a first solution, a background, now a background XB. You compute the solution emanating, model solution emanating that XB. When you do the variational assimilation, you compute successive XBs. But then you define first an objective function in which, when you change the control variable, the evolution of a difference between the solution emanating from the perfect state and the basic state is governed by the simplified law. And you do the minimization for that. You obtain a first minimizing state, XB1, for which we recompute a complete solution, and you redo the same thing. But you may add at this stage more physics or more things in the simplified law for evolving the perturbations. You have there many degrees of freedom on which you can act. And this actually makes the whole thing very efficient. Of course, the approach is very largely heuristic. It is one example as many others, that you have methods which are mathematically and theoretically well-founded, and when it comes to implement them in a real-life situation, when you must tune and do all sorts of heuristic arrangements. Very good example, but it turns out to be very efficient. So this is what is called incremental approach to variational assimilation. Okay, I'll stop. Thank you. Any questions? Yes, please.
Some questions regarding to this one, GK. You just mentioned that GK could be nonlinear.
The GK?
Yeah.
Could be what? Could be what?
Could be nonlinear.
Yes, it could be nonlinear. You can, for instance, you can keep advection by the field. You can keep advection by the wind field. It's a fundamentally nonlinear process because you have a product of the velocity by the gradient by the quantity that is advected. The evolution of temperature is given by dt of any quantity for that matter. dt over dt Eulerian plus u gradient of t, where u is the velocity and basically nonlinear because it's a function of both u and t, which are both model variables. So you may keep this nonlinear term in GK. This is what is done.
So you mean you just linearize one equation and keep another equation nonlinear?
You just simplify, you decide to ignore some components of the model, for instance the small scale, to ignore some components of the model when it comes to computing the evolution of a small perturbation to the small perturbation to a basic solution. You have a basic solution. We have a basic solution determined by the model. You have a basic solution psi. You have a basic solution of a form psi k plus 1 equals mk psi k. Well, psi k plus 1 is your whole model containing an incredible thing like clouds, water in its three phases, condensation, ice condensating and here, and you know, all kinds of things. Snow which becomes old, then it becomes less reflective. So the albedo of the ground changes because the snow, instead of being fresh snow, has been there for 2 weeks, and all this kind of thing, which are in models. But putting all of that, when it comes simply to compute over a 6-hour period or a 12-hour period, the evolution of a small perturbation to the model may be a waste of resources. And in a way, it is major work. So we may decide to ignore parts of the model. You may decide that this is what ECMWF does the small scale of a motion and to do the assimilation at a spatial resolution which is coarser than a full model. This is what we do. So that's the basic solution. And instead of taking for an exact perturbation, you put a perturbation delta psi t delta psi 0. And the exact evolution of a perturbation is d psi k plus 1 plus delta psi k plus 1 equal mk of psi k plus delta psi k minus mk of psi k with non-linear model. That's the exact evolution, like the exact evolution of a perturbation. Instead of that, it's like psi k plus 1 plus delta psi k plus 1 equal some equals, so equal to psi k plus 1 equal mk of psi k, yes, mk of psi k, plus, no, what did I write? No, that's this is the exact evolution. So, from which you get, take 1 equals mk of psi k delta psi k minus mk of psi k. This is the exact evolution of the perturbation for non-linear model. And this can be approximated to mk prime delta psi k. But adjoint method, which computes first order derivative, so which doesn't require the full exact evolution of the perturbation, but only the first the evolution of the perturbation to first order with respect to the initial delta x0 is big. In this is of place to prime delta psi k. In the first order approximation on which the adjoint method is exact. Let's say I repeat, but as far as computing first order gradient, this first order approximation is correct. Because
this is only in one direction. You need to do it multiple times. Multiple times to span all directions, because this is only in direction.
No, okay. Of course. No, I consider the perturbation of the evolution of one perturbation delta psi 0, independently of how you define and how many. But one perturbation. And the simplified GK tells that psi k plus 1 plus delta psi k plus 1 will be equal to mk of psi k plus gk. So I want to do that. In a sense, you say that the perturbation evolves independently. Instead of putting nk of psi k with delta psi k, you say psi k evolves according to the basic model. This has been computed before, and the perturbation evolves according to the simplified law. And then you have many. The advantage of the method is that here you have many degrees of. You can decide to put what you want in JK. To simplify your JK as you wish. Of course, you must simplify it in a way, but discards what is not very useful and takes what is really useful, of course. You may do it. You must do it in a way what is physically significant, but that's the way to do it.
Do you keep the same background covariance matrix when you propagate the G?
Oh, yes. Yes. And, well, yes. This is totally or largely dependent of what the background error. The background error covariance matrix is a statement about the uncertainty of the background. It is not a statement about how an initial perturbation will evolve. These are two different aspects. It just tells you my background is accurate to within some PB. Of course, that PB comes from the past, and the past has been established on the hypothesis on how error evolves. So things are related. But at the time when you do the simulation, these are two different pieces of information. The inserted of the background, which is a statement of how accurate the background is, and this, which is a statement as to how a small perturbation will evolve in the future. And the inserted of the background comes first, while how a perturbation will evolve is a statement relative to what you think as far concerns the future evolution of. So, what is what is called incremental approach. So in case you read somewhere the phrase incremental approach, or hear someone using that phrase, this is what it is. In fact, the word incremental is, I don't think it's very appropriate, because it amounts to simplifying the law, the dynamical law, which describes the evolution of a small perturbation. Of course, a small perturbation can be called an increment, of course.
Yes, question please.
Okay, another question. So you're talking about the nonlinear observation operator.
Yes. Yes, you can do something similar for nonlinear for the observation operator.
Yeah, because you also differentiate with that. I mean,
yes.
Take the Gato differentiation. You take the Gato differentiation to that. Then I think you have. I mean, in my understanding, we have no choice. I mean, that's actually just a kind of linear.
No choice on what?
I mean, you take the differentiation of your observation operator.
Yes.
Then I mean, we have no choice. I mean, but I mean, I just get just a bit confused because you said you take the tiny linear approximation and the forecasting of the weather system is not that good. I mean, especially for the small scale. I don't quite really understand. Is it because of the mathematics we simplify, or is it because
well, in a sense, we simplify or modify the mathematics in order to make things in this sense simpler, in order, in particular, to gain degrees of freedom on which we can play, which is very useful. We relax the total constraint as it appears from the theory, and this first allows economy in computing time, economy in writing of codes, but also gives degrees of freedom on which we can play empirically, largely realistically. There is no solid theory, but common sense, physical knowledge, need for having the forecast ready in time. It's a device. Yes, it's an ad hoc device, but which turns to be very useful. This amounts to changing the law which governs the evolution of a flow. Instead of using this exact law, given the model NK, we use a different law in which we separate these two into MK of psi k plus something. This of course is an approximation of the difference MK psi k plus delta psi k minus Fk of psi k. It's absolutely obvious. It's an approximation of that. And it's this quantity itself as one approximation, which is Nk Jacobian prime times delta psi k. The J of k is another approximation, J of k of delta psi k is another approximation of a difference. An approximation in which we may decide not to consider some features like the variation of the albedo of snow with time, which are very exactly legitimate if we do a 12-hour forecast, the 12-hour assimilation of a 12-hour period, because the variation of albedo of snow over a 12-hour period, although I remember very well, I mean, one day in the Glen Mountain in Australia, having begun skiing, we passed in the morning in the field which was full of snow, and when we came back in the afternoon, the snow had all melted. I've never seen that in Europe, but it had all melted. So within a few hours, the albedo had been significantly changed. But still, we may ignore this kind of effect in the temporal evolution of a small perturbation over a rather short period of time. There is even one extreme, which is to say that g of k of delta k equals delta xk. To say that the evolution does not change, the perturbation does not change in time. It is maintained. The basic solution evolves, but the perturbation of the basic solution does not evolve in time, which of course implies very much. And this is allowed to implement what they call, in the jargon of assimilation, F-GAT. Again, it was an expression people may very well speak of F-GAT, assuming that everyone in the audience knows what F-GAT is. F-GAT is first guess at the right time. What is what it means? It's the solution to a problem which Pavel has alluded to, that you may have observation between the 6-hour period, and you lump all these observations into one set, and then is it legitimate to consider that these observations performed at the time? Is it legitimate to consider it as performed at this time? So one way to do something less crude than just assuming that everything has been observed at the same time is to do that, because this will be compared with the basic solution at its own time. Although it will be considered that the perturbation doesn't evolve in time, the basic state evolves according to the basic law, and so the observation performed at time plus 2 hours with respect to the central time will be compared to the basic solution at time plus 2 hours, which is better than I compare it at time 0. So first guess at the right time, as fishy as it may appear, is the way to go, is an improvement of just lumping all observations over a 6-hour period at the same time. But with a rather drastic approximation, which is to assume that the perturbation does not evolve over 2 hours. The basic state may evolve, the perturbation doesn't. So an extreme case of incremental simulation. But it doesn't use yet that exists or has existed.
Okay. All right, yeah, good. In which case we